I'm Yuval, this is Omri, and this is Ruby. And we have 3 friends coming from Israel. We're doing reverse engineering, some of it for fun, some of it for profit. And like you just said, we're going to talk about the process of reverse engineering Broadcom Wi-Fi chipsets. This is a pet project we've been doing in the past few months in our spare time. And actually, it all began when we were visiting Ruby, and we forgot his wireless network password. It probably happened to most of you when you forgot your wireless network password, or your neighbor's wireless network password, or maybe the next coffee shop wireless network password. But whenever it happened to you, you had to take out the laptop, boot into your favorite Linux distribution, and run some cool Linux utils like REcon, wash, and so on. And we don't carry our laptops every day, all the time. And taking your laptop, it looks really lame when you need to capture some packets. So we thought of another idea. Why won't do it with your phone? The first thing that is good about it, click, is look at the left picture. This is the old method. And look at the right picture. It looks much more cool. And and after all, my super smart Android phone is already running Linux. It has a very impressive CPU, and it supports Wi-Fi, so why not? So we started this project with a dim vision. We wanted to run REcon and directly crack some networks off our phone, but we were not sure exactly what we want to do. So we took Ruby's phone. And at first, we found a teardown of this phone, and we learned that it was equipped with a chipset made by Broadcom called BCM4329. So we started exploring it like a simple Linux device. And whenever you start exploring a Linux device, the first thing you want to do is get a shell access to your phone. And this is what we did. And the first thing we did was to run iwconfig, which is a simple Linux utility used to configure wireless interfaces. More animation. And it sent us some meaningful information. The next thing we did was running TCP dump to capture some packets. And it didn't fail. But quickly we noticed some strange things. The first one is that our network device was called ETH0 instead of WLAN0, like a regular Wi-Fi interface. And the second thing is that it's an Ethernet interface for some reason. So it's not behaving like Wi-Fi interface, but it is Wi-Fi interface. So what's going on? So to understand how Wi-Fi interface should behave, let's talk a bit for who of you that don't know about how Wi-Fi works in general. Wi-Fi has 3 types of packets. It has data frames that contains data. It's a very simple packet. It just have a MAC address, some crypto stuff, and then IP, TCP, you name it. The other types are control and management. Control is not that interesting. It's mainly used to reduce congestions on wireless networks and flow control and things like that. And management frames contains some data about the available wireless networks, beacons, which are periodical advertisements of networks, association requests, association response, and so on. And what we see when we capture is we don't see any management or control frames. We see only data frames. And even that frame doesn't look like Wi-Fi at all. It looks like someone took the data portion out of the data packets and packed it as an Ethernet frame. And with our vision in mind of running REcon on our phone, REcon can't work with this packet manipulation because almost every Wi-Fi pawnage tool just needs the entire Wi-Fi packet and even packets sent to other clients and some packets that we don't get. So we wanted to see who does this, who throws frames or who translates packets from Wi-Fi to Ethernet. We know that somehow in the air the packets were surely sent as Wi-Fi frames, but when we captured it, it was Ethernet. So we had two suspects of who is doing this thing. The first one was the Broadcom chip, and the second one was the Linux driver that was communicating with the chip. And since the Android kernel is open source, we decided to start with researching the driver. So we began reading the kernel module's code, and we searched for a function that reads a frame directly off the chip. We wanted to see if the kernel is receiving Wi-Fi frames or Ethernet frames. And we quickly found the function you see on the screen, which does exactly this. Inside the ifdef, you can see a debug print that was turned off in the compiled version that they were using. But we wanted to turn it on and see what it prints. And actually, we turned it on, and we see a lot of printing information, a lot of debug prints, so much debug print that if we haven't cleared the dmessage log every few seconds, the phone would just fill its buffer and crash. So this is what we did. We cleared the dmessage every few seconds, and we looked at the dmessage and searched for this frame, for this incoming frame. And between the huge amount of data we received, we found it. And as you can see, it has a lot of hex bytes. But unfortunately, here is the Ethernet header, and here's the Broadcom header. There's not enough space for the whole Wi-Fi header in here. And it seems that the chip already sent the packet to the Linux as an Ethernet packet. So Linux is not the component converting this Wi-Fi to Ethernet thing. So not good. So we began researching why is this chip designed this way? And there are two approaches for implementing Wi-Fi chipsets. The first one is softMAC. In softMAC, the chipset is just a simple modem. It gets packet from the air and sends it directly to the Linux or to the CPU, the PC, without any manipulation. The CPU or the Linux is in charge of associating to networks, understanding beacons, and cipher things, and so on. And this is just a very simple way to implement a Wi-Fi chipset. On those chipset, tools like REcon don't have any problem running because they already have the full Wi-Fi packets and all of them. But the other approach is called FullMAC. It has better performance and better power consumption. And on FullMAC chips, the Linux doesn't have to know anything about Wi-Fi. The chip handles every Wi-Fi thing that it should do. And the Linux just say high-level things like, please scan for available networks, or please connect to network X or network Y, and whenever he wants to receive or transmit some packets, he just sends it as an Ethernet packet because it's very simple to implement. Well, this is clearly the case with our chipset, but it's not over. So knowing what's going on, we decided to take a look at the chip. And we've seen that REcon runs on some FullMAC chips, and we wanted to know how it does that. And the solution is towards monitor mode. Monitor mode, copied from Wikipedia, is a special mode of the Wi-Fi chip and the driver. And in this mode, you are guaranteed that as long as you're in this mode, the Wi-Fi stack is not doing any monkey business. No Wi-Fi to Ethernet conversion, no association with the Wi-Fi access point. It's just a simple modem. And there's another confusing term called promiscuous mode. In this mode, it means like telling the chip and the driver, don't filter packets for me. Just give me whatever you see. But it does not mean getting the packets in its raw form, so don't be confused. What we want to do is implement monitor mode and promiscuous mode. So doing this in softMAC chips is trivial. The OS just should not respond to any Wi-Fi stuff it sees. On FullMAC chips, sometimes monitor mode is also implemented, and it's just telling the chip go into monitor mode, and then it starts passing the full Wi-Fi packets. And this is what we want to do. So now we have a goal. We tried one of the easy solutions, which is to modify the driver. And we decided to contact Broadcom and say to them, hey, we want to implement monitor mode. Help us. We want sources. We can sign NDA. Just give us something. And we're still waiting for response for them. And after that failed, we realized that we are going to have to reverse engineer the chip. And when you begin reverse engineering project, the first thing you want to do is get something to reverse engineer. So we search for some firmware file loaded to the chip. And the first thing we want to do is get some of the firmware, then we're going to reverse engineering, and then patch it in some way to add monitor mode. So we looked at debug prints that we've seen before, and we can see that whenever the driver is loaded, it's loading some file to the chip, some file of the file system of the phone itself. And it's called FWBCM4329. So it sounds like the firmware. So now what we have to do is just detect what kind of firmware it is and start reversing it. Sounds pretty easy, huh? And, oh, sorry. So we have a file. Let's open it in a Hex workshop. And whenever we loaded, we guessed it was an ARM code. But what else can it be? But actually, we didn't have to guess because we looked at the specs of some newer chip, the next in the generation of chip, the 4330, and it's written there. It contains ARM Cortex M3 CPU. So, going back, we loaded the file to IDA, choose the ARM processor, and then we loaded to some 0 address. Well, we didn't know anything about it. And the first thing we see is some small 32-bit numbers at the beginning of the firmware. It's probably the interrupt vector table. What else can it be? And it makes sense. A lot of code in ARM mode. So we continue exploring it, and we discovered some other address table. That's address 100 hex. And it looks really good. So now we think we know how to start reverse engineering it. We know the architecture. We have the firmware file. But before we start reversing it, we need to see if we can patch it. And if there isn't any verification or authentication, and Ruby is going to talk about this part.
Whoa. Woo. Okay, so after breaking all the microphones, thank you, Yuval. So, as Yuval just said, the first thing we wanted to do is to make sure we could even patch the firmware in the first place. So we wanted to see that there is no firmware verification, no checksum, signature, etc. So remember the dmessage log that Yuval just talked about? Another thing that we saw there is that every time the firmware gets loaded into the chip, we see a debug print with the firmware version. And we easily identified this print in the code that we found. So we've decided to patch this print and replace the firmware version from what it was to BSimon, and it worked. So we discovered that there is no firmware verification at all, no checksum, no signature. We could just patch the firmware as we like. So we like that, and we wanted to continue looking at the code. We have around 250 Ks of ARM code, all in thumb. But more interesting is a special function table at 0x100. And in this function table, we see that we have lots of the function pointers pointing outside of our firmware file. And since there were lots of pointers that pointed to missing code, we wanted to extract this code. So we've tried to do some cheap probing ourselves to extract the missing region. We did extract some of it, but we wanted to do even better. So back to the debug prints. We saw that every time that the firmware gets loaded into the chip, there are a bunch of debug prints from a function that called DHDS-DIO membytes. And what this function does is that it loads the firmware chunk by chunk into the chip itself. Because the driver is an open source driver, we looked at the parameters of this function, and we've noticed that one of the arguments controls whether or not this function reads or writes the data into the chip itself. Okay, so with this new knowledge, we could just try to extract and read the missing region instead of writing it. So we looked at the function that loads the firmware into the chip and added our own pasten func after the process. By the way, pasten is the Hebrew word for ponage. So remember that. Okay, so in our pasten func, we've just read all the missing region in a loop using the same function that Broadcom uses in order to load the firmware into the chip. Okay, so it worked, and we've got all the missing region, and now our function table is complete, and we have hopefully all the code from the chip. Okay, so now we can go back to this monitor mode thing, but before that, let's talk about the region that we've just extracted. So now we have two regions. We have the RAM segment, which we can read and write, and we can modify it by changing the firmware file on the Android file system. The other segment is the segment that we've just extracted using the DHDS-DIO membytes function, and it's read-only. We cannot change it, but it contains lots of Broadcom code. So you might be wondering what Broadcom can do if they discover some broken code in the ROM segment, which is unchangeable. So it appears that Broadcom can fix their broken code in the ROM segment using the special function table that we've just talked about at 0x100 hex. They can do it because most of the functions in the ROM segment have a special wrapper, and what this wrapper does is it checks in the function table for a relevant fix and jumps to it if necessary. For example, if Broadcom discover a bug in their memset implementation, they can just update the memset pointer in the function table, and that's way all the memset calls will jump to their new memset implementation. This was very crucial to us because it allowed us to patch what was otherwise read-only code. Okay. So back to debug prints. Everybody loved debug prints, even Hugo. In our case, we didn't have many debug prints, but we had one debug print that helped us a lot. It was a watchdog-related debug print, and we've Googled it, and we found it on another Broadcom softmac driver for the same family of chipset that we were working on. And it helped us a lot because it gave us function names that we didn't have on from the debug prints on the chip itself, and some other helpful stuff to understand some of the Broadcom code. Okay. So at this point, we don't know. We still don't know much about the firmware itself, and we're trying to find something to hold off, some starting point where the chip gets a raw Wi-Fi frame before any translations occurs. And what you can see now on the screen is called an LLC header. And every Wi-Fi data frame out there contains this LLC header. So we looked for this LLC header, and we found about a dozen references to it. And we tried to look at them one by one in order to find some starting point where the firmware gets a raw Wi-Fi frame. Okay, so how do we check them? So we write a small detour that does some trick before the original function starts and does some trick after it. And we write this simple detour in ARM assembly. We assemble it, we get some bytes, we take those bytes, we put them back with our favorite hex workshop back to the firmware, and we load the firmware into the chip. But in this way, we can't, because the chipset doesn't have any debugging mechanism that we know, it doesn't help us to see the buffers in the function that we're looking for. So what we actually are doing is we're copying the suspect buffer from the function to the end of the stack, and then we want to read it using the same function that we've used in order to recover the missing code region. But in order to do so, we need to patch the kernel for every new patch that we write. For example, if we have a bug, let's say here, then we get a kernel panic. And we don't like this process. It's very long and error prone, and we want to do something in order to continue our research more easily, because we don't have much time to work on it. So we decided to write two research tools, one in order to help us with binary patching, and one that will help us in the kernel to avoid the kernel patching each time. The first thing we did is to write a simple Python script called a generic patcher, which wraps all the binary patching tasks and allows us to write simple detours and any other patch in C instead of in assembly. This is an example of how it works. What we need to do is just to put the destination address for the resulting patch in the firmware, give it the C source file, and state the maximum size for the patch, and that's it. This is an example that if you run it, you'll get a new firmware with the new patch inside of it. Among other types of patches, we also implemented simple assembly patches, even fixing a relative jump in some given branch, replacing a function pointer all over the firmware, and last but not least, inserting an invalid opcode that when the chipset execute this invalid opcode, it dumps lots of debug information in the dmessage log. Okay, so now we fixed all the binary patching part, but we still have to compile the kernel for each new patch that we write in order to extract the memory out from the chip back to the OS. So we don't like that because we write bugs in the kernel. We're not so good at programming. So we've decided to expose the kernel function that we use in order to read and write the memory chip. This is an example of an output that we did from user mode after exposing the DHD SDI or membyte function. And that's it. Now we have some new tools that we can use in order to find the first place that gets a raw Wi-Fi frame in the chip itself. So back to those LLC header references. We now using the new tools, we could go over them one by one. For each one, we guessed which parameters have the raw Wi-Fi frame inside of it. Long story short, we quickly found the place that really gets the raw Wi-Fi frame. This is a function called WLC BMAC receive, and this is actually the first raw packet that we've extracted from my phone. This was a very happy moment for us. But soon we realized that it's not enough because our method of extracting the raw Wi-Fi frames is slow and impractical for any Wi-Fi pawnage because it's so slow. So what we really wanted to do is to find how the chip usually sends packets to the OS, and not by copying it to the end of the stack and reading it by the Broadcom function. Okay, so long story short, we discovered using our new tools that the function WLC BMAC receive gets the raw Wi-Fi frame by calling a function that's called DMAREx, and then oh, oops. Wait a second. I'll go back. Okay. Okay, so we discovered that the DMAREx is the function that gets that returns the real raw Wi-Fi frame, and we discovered a bunch of other functions that are getting called from WLC BMAC receive, and we discovered the function that sends the translated packet back to the operation system. So after knowing the function that receives the first the raw Wi-Fi frame and the function that sends the translated function back to the OS, we could just connect those two functions and get monitor mode up and running on my phone. But as you can see, we have some problem. All the packets that we receive are broadcast packets, and actually we're not really in monitor mode because in this way you can't do any Wi-Fi pawnage, and we don't like that. So we've guessed that what we needed to do is to find some way to put the chip into promiscuous mode. And we guess that in order to do so, we need to set some flag that will put the chip into promiscuous mode. Luckily for us, we found some interesting flags in the other Broadcom driver that we found using the debug prints. And in those flags, we found a flag that called MCTL promisc. And we also found a function that plays with those flags. And indeed, after changing the flag, we got monitor mode up and running on my phone. and we were very happy. And okay, but that's not it. Now we've implemented monitor mode. It's not enough, because in order to do some real Wi-Fi ponage, you also need to be able to inject packets, and Ildis is going to talk with you about that. Okay.
Hi. Can you hear me? Okay. Okay. So at this point, we had some packet sniffing ability, and we were able to crack web networks, but this is a slow process. Cracking web is very slow, especially if you can't inject packets, and you can't pawn WPA networks or WPS-enabled networks, and basically you can't use any of the new, smarter, faster attacks that are out there. So we wanted to add packet injection support to our firmware, and in order to do that, we first needed to update our research infrastructure once more. Well, basically, when we asked ourselves how can we find how to packet inject as fast as possible, the best answer we could give ourselves was that we want to send packets up into the air using the normal method and see what functions gets called. And if we'll have all those events on a single timeline, we can send a bunch of packets from different types and then see what functions gets called and see what the correlation is, see what function gets called after every packet we send. And this would be a great candidate to send packets up to the air ourselves. So we went on and wrote firmware that can log both packet sends and function calls on the same timeline. I could tell you exactly how it works. I will, I promise. But I think it would be best to first show it. So let's see this framework in action. We have Nexus 7 over here, and using our framework hands-free, we'll upload the firmware to the chip. What this firmware does is checks one of our hypotheses. We had a candidate function, and we wanted to check whether it gets called when we send pings up to the air. So we've uploaded it, and now we're sending pings. And the next thing we see is a Wireshark log of what went on through the chip at the same time. So as you can see both the ICMP packets that you would expect to see if you send pings, and the MITS packets. MITS is our log packets, and it contains a lot of useful information. For example, it contains the raw packet buffers, the SK buffs you might know from Linux. And it contains the function arguments we've passed to it and a stack trace. So we can not only see what function got called, but how did we get there? What's the entire flow that got us to this function? And this gave us a lot of information about how the firmware works, and it allowed us to check many functions at once. It allowed us it gave us a lot of diversity in our research, and well, just sped up the process tremendously. Give us okay. So let's go back to the presentation. I think. No. Okay. Great. So using this infrastructure, we could do all of the stuff we already talked about. Stack traces, real-time packet sniffing. It's all on the same timeline, so we can see the order of events, and we can get the stack trace. So we can, by monitoring one function, we can get the entire flow that got us to it. And how it works basically is that we generate a new patch using our generic patcher. We add a call to our new function called mylog. Yeah. It's a very unique name. And then we upload it to the chip. Now the chip is up and running, sending packets into the air, does whatever Wi-Fi chip do. And at this point, we fire up TCP dump and start sniffing those packets. And what we're sniffing are both packets and log events. Actually, we're exploiting the fact that we now know how to send raw Wi-Fi packets back to the operating system in order to send our own generated log packets along the way. Then we fire up Wireshark and see all the cool stuff you saw earlier. This infrastructure was really cool. It helped us a lot. And with it, really quickly, we went through all of our candidate functions to inject packets and found the correct one. And now we're able to inject packets. Great. Now our monitor mode is fully running. Well, we can use all the Wi-Fi ponage tools like River, Wash, Bestside, you name it. It could all run on Ruby's phone, and we were very happy about it. There was only one problem left. At least we thought there was one problem left. It only worked on Ruby's phone. I mean, I didn't join this project so that Ruby could hack Wi-Fi networks and I would sit aside, play Angry Birds with my phone. I wanted to hack Wi-Fi networks myself as well. And I had a different phone. I had the Galaxy S2, which had a different chipset, the BCM 4330, and not the 4329. So we went on to research this chip as well. We figured it wouldn't be too hard. We would just port the same tricks and do them again on the new chipset. And the first trick was extracting the missing region again. Remember the ROM region that we've extracted using the driver? So we tried doing the same thing again, and it failed. Well, it miserably failed, so we double-checked ourselves. We tried reading from the RAM again, and it worked, and we tried reading from the ROM, and it failed again. So at this point, we were pretty sure it wouldn't work. And we figured there must be some kind of protection that prevents us from doing this. And this protection might stop us from reading this memory region through this function, but we weren't too worried because we knew that the chip itself had access to this memory region because there were function pointers pointing to it. Well, it can't be that it doesn't have access to it. So we figured, okay, what we would do is we would find an empty spot on the RAM that contains something that's not that important, and we would push our copy stub somewhere that gets called along the driver, along the initialization of the chip, and that copy stub would copy the code from the ROM region to the RAM region, and then we would read it using the same method again. So what's left to do at this point is find an empty spot. So we dumped the entire RAM of the chip and started looking for an empty spot to copy our code to, or their code to, more exactly. And very soon afterwards, we found one. We found a spot like that. For those of you who can't see, which is second row and back, it's written cats, which is the little Indian word for stack. So we figured this must be the unused top of the stack. And if it's unused, we can put it to our own use to extract this missing region. So we found the part in the code that initializes this stack. It was pretty easy to find. It was written stack as well. And then we injected our code over there that would copy the ROM section into the RAM section. And we've extracted the missing region using this method. Great. Now we have all the new chipsets code as well, and we can port the patches to this firmware as well. Actually, this was pretty straightforward. There weren't any other challenges along the way. So very soon after extracting the code, we had support for other chipsets as well, and we've added support to two other chipsets, the 4330 B1 and B2. And our solution currently looked something like this. we had the Wi-Fi chip, which we've patched in order to stop it from filtering our packets and stop it from stripping away our Wi-Fi header and leave them as they are. And we've patched our kernel module as well. Well, the reason we did that is in order for it to pass those packets along and to report being in monitor mode, because it would report being in manage mode. And our tools look for that monitor mode in order to work. So we had to change this as well. But the tools themselves, the arrow dump, for example, was left untouched. It was the original arrow dump straight from the SDN. And this was a fact that we liked very much, because it means that if any one of you would think of a new Wi-Fi pawnage tool or some cool things to do with raw packets, he could just compile it, not knowing anything about our monitor mode, and just use it on his phone as well. It looked very cool to us. So we thought by this point that we're done, and we have updated this solution to our blog and published it. And it got some traction, and people were interested. And very soon we found out that, well, it might not be as good as we thought, because compiling each kernel takes a lot of time, and you had to recompile the entire kernel, because most of the time the Wi-Fi module was embedded to the kernel and not as a standalone module. And we are already supporting 3 chipsets, which exist in about 100 Android device types, and each device has way more than one kernel. So we would never be done with compiling and supporting all these chipsets for everyone who wants it. And we wanted to help other people to use our solution as well, because it was already out there, and we wanted people to use it. And so we figured that the kernel module patch must go. We can't allow ourselves to patch the kernel module. It's too much work. We don't have the time to do it. We have better things to do with our time, like, I don't know, nothing. And and this wasn't good enough. But we also didn't want to patch AeroDump. We liked it being unpatched. And we had to find a solution that leaves both of those parts unpatched and still works. And what we chose to use is LD preload. I'm sure most of you know this, but LD preload is a generic hooking method for Linux. You set up an environment variable, and then you can replace any function that you want. And what we chose to replace was IO control. The IO control function is the function that is used to pass control messages to the driver, and we just faked the answers. When a program asked, excuse me, am I in monitor mode? We just said, yeah, monitor mode is fine. And when the program asked what's the MAC address format, we said, yeah, it's Wi-Fi. It's not Ethernet, it's Wi-Fi. It's a Wi-Fi packet, because we knew what we were sending from the chip. We knew these were Wi-Fi packets, so it's fine to just replace the driver's answer with the correct one. So our new solution is no kernel module patching. We had the Wi-Fi chip still patched, of course, and the LD preload did the job for us instead of patching the driver. And now our solution, we think it's almost idiot-proof. I mean, anyone with a rooted phone and the correct chipset can use it. And we're going to do a test on this assumption, and we have an idiot ready here. Yeah. So and we're going to try and use this APK. Let's no. Okay. Okay. We have the Nexus 7 screen broadcasting to the computer, and we've wrapped. Since we don't need any kernel module patching anymore, we've wrapped this entire thing in an APK as an Android application, which you can just install, and it would ask you if you want to install the firmware, and then you enable monitor mode. It takes a bit of time because you upload the entire firmware to the chip and let it start running and stuff. And then you can just, I don't know, run error dump, whatever you'd like. And voila. We're sniffing this entire thing. This is great. But actually, this is faking it. We said we could packet sniff a long time ago. We need to show you we can inject packets as well. So let's run Beside or some more impressive tool. And so anyone downloading something important, we're so in advance. And okay. And it's their thing. Great. And so now I hope you believe me. We can package index as well. And okay, yeah, we can close it now. Yeah, we own the REcon CX. We have something to brute force at home, and great. This is a fully working Android application, which will release at the end of this presentation as a closed beta for you guys, but still. And yeah. Okay. Great. And at this point, we're supporting a bunch of chips, and we can support the other chips as well. And we don't think it would be hard. We're just busy making this presentation. We're pretty sure we're done with all these monitor mode solutions, and we wish to share the lessons we learned along the way, because this is what these conferences are about. So the first lesson we learned is that the research infrastructure matters. You all know this part when you think, well, this is going to take me a few minutes, and let's just do it by hand, and then 2 weeks later you just keep doing it by hand, and it's still not done, and you've wasted a lot of time on human errors and being tired errors and typos and stuff like that. Write your infrastructure as soon as possible. It helps a lot. It saved us a lot of time, and it allowed us to do things we wouldn't be able to do otherwise. Like, for example, the Wireshark debugging. I mean, we couldn't check our assumptions as fast without these infrastructures, no matter how good reversers we are. Well, this is the first lesson. The second lesson is related to the fact that we only worked on Ruby's phone. We had it fully working over there, and then only then we went on to research MyChip. This was a huge mistake. Well, when we opened MyChip's firmware, we found out a lot of debug strings, a lot of function names, a lot of stuff that could have made our lives so much easier, and we missed them because we worked depth first and not using all of our information. And well, the third lesson is that we actually weren't expecting to find source codes for this stuff, and we still did. I mean, it's a closed source chip. It's not Linux related in any way, and we still found sources. So I don't know. It was better than any decompiler could have done. We had flag names, and it helped us a lot. I don't know. I guess it's a bit of a cliche, but Google is your friend or something. Well. These are the main lessons we learned, and it's also worth mentioning Monomob, which is a different group that worked on Broadcom's chipset in parallel to us. We didn't know about them; they didn't know about us. They also made some work on the iPhone devices, and well, this is pretty much about monitor mode. Well. At this point, we were fed up with monitor mode a bit, and we thought of doing something completely different for a while. We thought, well, we're already modifying the firmware, and we're doing all this stuff that it shouldn't do. Why not try and do some evil stuff as well? Well, evil layer, I don't know, stuff like that. We thought, well, okay, well, what we have here is basically man in the middle, because we're at the chip level receiving all the packets that the phone sends and all the packets that it receives, and we can change whatever we want along the way. And so what can one do with such a thing? Let's say our application wants to surf to Black Hat, because, I don't know, it has its reasons. And it asks the operating system, please give me Black Hat's IP address. And it sends this down to the operating system, which says, oh, I don't know where Black Hat is. Well, let's send out a DNS packet. And it sends the DNS packet down to the Wi-Fi chip, and the Wi-Fi chip then do whatever it wants with it. Our POC does exactly that. It sends DNS packets to our server and allows us to divert whatever part of the traffic that we want from to our own servers. And you don't have to believe me. I will show you a demo now. Basically, this is only a simple POC. You can obviously, the people in this audience can obviously think of a lot of uses to such modification. And okay, this proves, I guess, we have internet connection. You can surf to Hackaday and stuff like that. And now we can surf to Black Hat as we promised. And let's see what happens. Tom, tom, tom. Well, and I was starting to speak about what's cooler about this than just kernel mode modification is the fact that it's always transparent, totally always transparent. I mean, if you would sniff the packets, if you could zoom, if you would sniff the packets from inside the phone, you wouldn't see any difference. You would see the DNS packet going to the same server all the other DNS packets went to, and the response coming from the same DNS server all the other packets got from. And I guess just raising the bar for detecting such rootkits or malware, because it sits lower along the chain. And well, we would like, if you have cool ideas for what else can we do with it, we'd be happy to hear them. Great. So, demo. No, we did that part. Okay. What out of all this you can get? You can get the generic patcher. It's in GitHub. It's the firmware we use to patch our firmware. It's available. You can collaborate, add your own patch types. We'd be happy that this infrastructure would get better. You can get the Android app. It's at Google Code. You can download it. And well, we are planning to release a lot more stuff in the near future. You can check out our blog. And there would be updates. And you can contact us at contactbsimon@gmail.com or just come talk to us. We're here. Great. This is mostly it. Any questions? Yeah. Okay. The question was, what's the portion of time we spent on, if I heard correctly, we spent on writing infrastructures like Wireshark debugging and I don't know, patching infrastructure, opposing to reverse engineering in IDA stuff like that. The time frame, basically, this entire project went on our spare time. It took us about 3 weeks, I think. Out of it, I think more than half went on the infrastructure. But I think I'm not sure this is the correct comparison, because what you want to measure is how long would it take you to reverse engineer it in IDA if you didn't have the infrastructure. And in that case, I think it would have taken us at least, I don't know, 3 months, 2 months at least, because there is a lot of code out there on that chip, and most of it isn't relevant, but it's hard to tell because you don't have an entry point, you don't have a debugger, you're having a hard time seeing what's going on inside it. So this is the comparison I think is relevant, and I think it saved us more time than it took to build them. And for example, the generic patcher took 2 or 3 hours to write, and the individual frameworks didn't take a lot of time. It was the state of mind of thinking, what tools do I need to solve this problem that led us to writing them. I hope I answered it. Yeah. Thanks.
I have a question/possibly a suggestion for future something. I was curious if you looked at the other chips that are made by REcon, the ARM architecture, like their embedded security module, smart card readers,
No, it's cool. Maybe we'll look into it, but no. Yeah, we are also interested, if you mentioned it, this chip does more than Wi-Fi. It also does Bluetooth and FM receiver, transceiver, depends on the specific chip. And we were also interested in looking at the chip's other cores and trying to see if we can do stuff with them as well. I think we might try and do it in the future as well. Yeah. The question was if we found a way to enable monitor mode without patching the firmware. We don't know of any such way. We didn't find any, but to be honest, we made a basic search and then figured it would be faster to find where to hook the firmware than reversing the entire firmware searching for monitor mode. Because we knew better what to look in patching than in enabling. Yeah. The question was if we have to patch the firmware each time we reboot the device. Currently with the APK, I mean, it's not the firmware. Yeah. The firmware is a file sitting on Android's operating system, and you can either replace the file or just tell the driver to load it from elsewhere. But basically, it's running from RAM memory section. So it's not written to the chip's ROM in any way. Do you want to answer that? You looked at it a bit.
To answer that, the only way you could do it is by replacing the file in the. Okay. So the question was if we could do any persistency with the rootkit inside the firmware itself, and if you will replace the firmware in the file system, then you'll get persistency. But if someone will update their firmware, then the original firmware will get back in place. So you must, if you want to keep your firmware there, we don't know of any way to do it yet.
Yeah, well, we don't know. It looks like a ROM section. We didn't see any update mechanisms. We didn't see any broadcast updates to the ROM section. Well, there might be, but we don't know of any. Yeah, we didn't thoroughly search for one. Yeah. For now, we're sharing the patching infrastructure, but not the tool updating. First of all, it's really a mess, and if you're not going to research this chip, it's not going to be of any use to you. If you are, any of you want to, if you do want to research the chip itself, you can come talk to us, and we'll share it with you. I'm sorry, I didn't hear the question. Are there any hidden functions that we found interesting to play with for more time? We were basically really goal-oriented during this time, and we did it in our spare time, so we had to be in order to complete it. But I don't know. Maybe there are. Okay. Thumbs up. You can come talk to us later if you want.